Iron ore definition. Iron ore is a crucial raw material in the production of steel, making it an integral part of various industries worldwide. It is a naturally occurring mineral or rock containing iron compounds, typically with iron oxides such as hematite and magnetite being the most common forms. These iron oxides are often accompanied by varying amounts of other elements such as silica, alumina, and phosphorus. The extraction and processing of iron ore involves several stages, starting with its exploration and mining. Iron ore deposits are found in various geological formations, ranging from sedimentary to igneous rocks. Once a suitable deposit is located, mining operations commence, which can involve open pit or underground mining methods depending on factors such as the depth and accessibility of the ore body. After extraction, the raw ore undergoes beneficiation, a process that involves crushing, grinding, magnetic separation, and sometimes flotation to separate the iron-bearing minerals from the gangue minerals. This step is crucial for increasing the iron content and reducing impurities in the ore, thus improving its quality and suitability for further processing. The processed iron ore is then transported to steel mills or smelters, where it is converted into various forms of iron and steel products through a series of refining and smelting processes. The most common method is blast furnace smelting, where iron ore, coke, a form of coal, and limestone are heated in a blast furnace to produce molten iron, which is then further refined to remove impurities and adjust its composition as needed. Iron ore plays a significant role in the global economy, as steel is essential for the construction of infrastructure, transportation, machinery, and countless other applications. Therefore, the demand for iron ore is closely tied to industrial activity and economic growth. Major iron ore producing countries include Australia, Brazil, China, India, and Russia, with significant reserves also found in countries across Africa, North America, and Europe. However, the iron ore industry faces various challenges, including fluctuating commodity prices, environmental concerns related to mining activities, and geopolitical factors affecting trade dynamics. Furthermore, there is ongoing research and development aimed at improving efficiency in iron ore extraction, processing, and utilization, as well as exploring alternative sources of iron such as recycling and alternative iron-making technologies. In summary, iron ore is a fundamental resource that underpins modern industrial society, serving as the primary source of iron for steel production and contributing to the development and advancement of various sectors globally. Its importance underscores the need for sustainable practices and innovations to ensure its availability and responsible utilization for future generations. Formation of iron ore. The formation of iron ore deposits is a complex geological process that spans millions of years and involves various factors such as geological settings, chemical reactions, and environmental conditions. Iron ore deposits can form through several mechanisms, including sedimentary, igneous, and metamorphic processes. Here's a detailed exploration of each. Sedimentary iron ore deposits. Sedimentary iron ore deposits are the most abundant type and are formed by the precipitation and accumulation of iron-rich sediments in ancient marine or terrestrial environments. The process begins with the erosion of pre-existing rocks, which release iron-bearing minerals into rivers and streams. These minerals are then transported by water currents and deposited in low-energy environments such as lakes, swamps, and shallow seas. Over time, the accumulated sediments undergo compaction and cementation, transforming into sedimentary rocks known as iron formations or banded iron formations, BIFs. These formations typically consist of alternating layers of iron-rich minerals, such as hematite or magnetite, and silica-rich minerals like chert or jasper. BIFs are often found in Precambrian-aged rocks and are a significant source of iron ore globally. Igneous iron ore deposits. Igneous iron ore deposits originate from the crystallization of magma or lava enriched in iron and associated minerals. These deposits are relatively rare compared to sedimentary iron ores but can still be economically significant. One common type of igneous iron ore deposit is known as magmatic hydrothermal ore deposits, which form when hot, metal-rich fluids are injected into existing rocks and precipitate iron minerals as they cool and solidify. Another type of igneous iron ore deposit is layered mafic intrusions, where layers of iron-rich minerals such as magnetite or ilmenite accumulate within large igneous bodies like layered intrusions or flood basalts. These deposits are often associated with volcanic activity and can be found in regions with extensive igneous activity, such as rift zones and continental hotspots. Metamorphic iron ore deposits. Metamorphic iron ore deposits are formed when pre-existing iron-rich rocks undergo metamorphism due to changes in temperature, pressure, and chemical conditions. During metamorphism, the original minerals in the rock may recrystallize or react to form new minerals, including iron oxides and sulfides. Metamorphic iron ore deposits can occur in a variety of geological settings, including regional metamorphic terrains, contact metamorphic zones, and shear zones. The intensity and duration of metamorphic processes influence the composition and quality of the resulting iron ore deposits. In summary, iron ore deposits form through a combination of geological processes that vary depending on the specific conditions and environments involved. Understanding the formation of these deposits is essential for exploring, evaluating, and exploiting iron ore resources effectively. Geologists use various methods, including field mapping, geochemical analysis, and geophysical surveys, to study the origin and characteristics of iron ore deposits and identify potential areas for mining and extraction. Characteristics of iron ore. Iron ore exhibits a variety of characteristics that influence its suitability for various industrial applications and its value in the market. These characteristics include its chemical composition, physical properties, mineralogical structure, and geological formation. Here's a more detailed exploration. Chemical composition. Iron ore primarily consists of iron oxides, with hematite and magnetite being the most common minerals. The chemical composition of iron ore also includes varying amounts of other elements such as silica, alumina, phosphorus, sulfur, and trace elements like titanium, manganese, and vanadium. The presence of impurities can affect the ore's quality and suitability for steelmaking, with high levels of contaminants often requiring beneficiation processes to improve purity. Physical properties. Iron ore exhibits several physical properties that influence its handling, processing, and utilization. These properties include its density, hardness, particle size distribution, and magnetic susceptibility. The density of iron ore typically ranges from 3.5 to 5.5 grams per cubic centimeter, depending on the mineralogy and porosity of the ore. Hardness varies among different ore types but generally ranges from relatively soft to moderately hard. Particle size distribution is crucial for efficient processing, with finer particles often requiring additional grinding and beneficiation steps. Magnetite ore exhibits magnetic properties, allowing for magnetic separation processes to concentrate the iron content. Mineralogical structure. Iron ore occurs in various mineralogical forms, including hematite, magnetite, goethite, limonite, and siderite, among others. Each mineral has its own crystal structure, physical properties, and chemical reactivity. For example, hematite and magnetite are commonly found in banded iron formations, BIFs, and are the primary sources of iron for steelmaking. Goethite and limonite are hydrated iron oxides formed through weathering processes and are often found in lateritic iron ore deposits. Understanding the mineralogical structure of iron ore is essential for processing and beneficiation purposes. Geological formation. The geological formation of iron ore deposits influences their size, shape, distribution, and ore quality. Iron ore deposits can form through sedimentary, igneous, or metamorphic processes, as described earlier. The geological setting, including the type of rock, tectonic activity, and depositional environment, plays a crucial role in determining the characteristics of iron ore deposits. For example, sedimentary iron ore deposits like banded iron formations, BAFs, often occur in ancient marine environments, while igneous iron ore deposits may be associated with volcanic activity and magmatic processes. Understanding these characteristics is essential for the exploration, extraction, processing, and utilization of iron ore resources. Geologists, metallurgists, and engineers use various analytical techniques, including chemical analysis, microscopy, X-ray diffraction, and magnetic susceptibility measurements, to assess the quality and properties of iron ore and optimize its utilization in steelmaking and other industries. Additionally, ongoing research and technological advancements aim to enhance the efficiency and sustainability of iron ore processing and beneficiation processes. Iron ore types. Iron ore encompasses various types distinguished by their mineral composition, geological formation, and physical properties. Understanding these types is crucial for mining, processing, and utilizing iron ore effectively. Here's an in-depth exploration of the different types of iron ore. Hematite. Hematite is one of the most abundant and widely distributed iron minerals, characterized by its red to reddish-brown coloration and metallic luster. It has a chemical formula of and typically forms in sedimentary environments, including banded iron formations and sedimentary beds. Hematite is often considered a high-grade iron ore due to its high iron content and low levels of impurities. It is a major source of iron for steelmaking and is commonly found in countries such as Australia, Brazil, and China. Magnetite. Magnetite is another significant iron ore mineral, known for its black coloration and strong magnetic properties. It has the chemical formula and occurs in a variety of geological settings, including igneous rocks, metamorphic rocks, and hydrothermal veins. Magnetite ore is often associated with layered mafic intrusions and can form massive ore bodies known as magnetite skarns. It typically contains higher iron content than hematite but may also have higher levels of impurities. Magnetite deposits are widespread globally, with major occurrences in Australia, Russia, and Sweden. Goethite. Goethite is a hydrated iron oxide mineral with the chemical formula. It commonly forms as a weathering product of other iron-bearing minerals, such as hematite and magnetite, through the oxidation and hydration of iron-rich rocks and ores. Goethite often occurs in lateritic iron ore deposits, including bauxite deposits, and is characterized by its yellow to brown coloration and earthy appearance. While not as economically significant as hematite and magnetite, goethite contributes to the overall iron ore reserves and may be processed alongside other iron-bearing minerals. Limonite. Limonite is another hydrated iron oxide mineral, similar to goethite, with the general formula. It forms through the weathering of iron-bearing minerals and is commonly found in soils, bog iron deposits, and sedimentary rocks. Limonite exhibits a yellow-brown coloration and often occurs as botryoidal or stalactitic masses. While not a primary source of iron for steelmaking, limonite may be processed for its iron content in regions where other iron or minerals are scarce or economically inaccessible. Siderite. Siderite is a carbonate mineral with the chemical formula, containing iron in the ferrous state. It forms under reducing conditions in sedimentary environments, such as marine and lacustrine sediments, as well as hydrothermal veins. Siderite typically exhibits a light to dark brown coloration and may be associated with other carbonate minerals such as calcite and dolomite. While less common than hematite and magnetite, siderite can serve as a source of iron ore in certain geological settings. These are some of the primary types of iron ore, each with its own distinct characteristics and geological occurrences. Understanding the differences between these types is essential for prospecting, mining, and processing operations, as well as for optimizing the efficiency and sustainability of iron ore utilization in various industries. Additionally, ongoing research and exploration efforts continue to uncover new deposits and expand our understanding of iron ore resources globally.